The objective of the third compository assignment is to design a boundary scan architecture for a 3-input and 3-output circuit. It supports the mandatory boundary scan infrastructure X-test, bypass, and sample preload, and the optional override boundary scan instruction. Override forces a given logic value to any output pin, while the remaining pins operate normally. It can be used to validate fault tolerance features in mission-critical systems. Part of the task was also to learn how to use a free-running clock for the flip-flops. Boundary scan is a method of structural testing and of digital printed circuit boards. It came as a solution to some problems. Functional testing struggled with the complexity of more complex integrated circuits. And in-circuit testing struggled with small outline surface mount devices and advanced mounting technologies. Boundary scan solves this by enabling direct access to any PCB node without backdriving effects. It became standard in 1990 and has become very popular and used for other purposes as well. First, we'll do a brief walkthrough of the process of making the boundary scan infrastructure. Details will be explained later in the video. We started out by designing a simple flip-flop and a 2-to-1 mux, and used them as building blocks when designing the boundary scan cell. We implemented 6 boundary scan cells to make out the boundary scan register, mapping all the ports according to the description of the boundary scan standard. Next, we designed an IR cell and an IR register and a bypass cell, followed by the instruction decoder and the tap controller. We read a lot and asked quite a few questions before we figured out how we should connect all the control signals, but figured out that once we got started it wasn't such a big deal. We connected the signals to the different muxes, and after a few minor edits we got it working according to the predefined test bench. And then we implemented the override settings as explained in detail in the end of this video.
Or test access port. It's a finite state machine and a very important block, as it controls the operations of all the other blocks. The tap controller has 3 main functions: loading the instructions in the instruction register, providing control signal to load and shift the test data into TDI and auto TDO, and performing test actions such as capture and shift. The operations is controlled by a series of 1s and 0s that comes from the TMS pin. TMS is short for test mode select. When powering up, it will start up in test logic reset state, and all the BS cells will be in transparent mode. It remains here as long as TMS is high and the circuit is in normal operation mode. As soon as TMS changes to logic 0, the controller is in the run test idle state. It's awake but does nothing. To start testing, the instruction needs to be loaded into IR. For this, TMS is held high and it takes 2 clock cycles for the controller to reach the select IR scan state. From here, we can move through the various capture IR, shift IR, and update IR states as required. The last operation is the update IR operation, and at this point, the instruction loaded into the shift section of the IR is transferred to the hold section to become the current instruction. This causes the IR to be deselected as a register connected between TDI and TDO, and the data register identified by the current instruction to be selected as the new target register between TDI and TDO. Then we can manipulate the target data register with a generic capture DR, shift DR, and update DR control signals. If there is a need to reinitialize the controller or turn off the override instruction, it can be done by holding TMS high for maximum 5 clock cycles from anywhere in the state machine.
The boundary scan cells has two main parts, the capture shift side and the latch side. This design allows us to hold the value in the flip-flop while we shift in the new values in capture shift side. Each side is built with a combination of multiplexers and D flip-flops. The first multiplexer on the CS side is either parallel input, the normal circuitry, or serial input, the boundary scan circuitry. The control signal is the tap shift DR signal. The second multiplexer is the one that allows us to use a free running clock. That is controlled by tap shift and tap capture DR signals. The next follows the first D flip-flop. This takes the clock and the input from the second multiplexer, and the output goes to the serial out and as an input to the first multiplexer on the latch side. The first multiplexer here is the free running clock enabling multiplexer again. This is controlled by tap update DR signal, and the output from that goes into the second D flip-flop. The next multiplexer is controlled by the X test on signal from the instruction decoder. That decides whether or not to let the normal parallel signal through. And the last multiplexer is an extra multiplexer to enable the override instruction. This normally lets the circuit work as usual, but if the override is enabled, it chooses a value from the override register. The instruction register cell is basically the same as the BSC without the two last multiplexers. This is also controlled by IR signals from the tap controllers. It features the same capture shift stage and a bit simpler latch stage. The instruction register is meant to hold the instruction that is shifted in from TDI and will set the behavior of the circuit along with the tap controller. The BP or bypass register is also quite similar but even simpler. The bypass is enabled by default, simply letting TDI through to TDO. It has the same capture shift stage but no latch stage. And this input is either TDI or ground or zero. And it's controlled by DR signals from the tap.
The task of the instruction decoder is to take input from the TDI and translate them into instruction and create the control signals. In the instruction decoder we first check if the ERD reset is set to 1. If this is true, X test, sample, preload and override is set to 0, but the bypass is set to 1. When the bypass instruction is initiated, the bypass register is placed between the TDI and TDO pins. If the ERD reset is set to 0 and the ERD cells is set to 0, 0, 0, the X test is initiated and the instruction selects the boundary scan register. The X test instruction uses the boundary scan cell to test the connection between the two devices and search for open and short damage of the device. When the ERD cells is set to 1001, the sample preload instruction is initialized and selects the boundary scan register when executed. The instruction sets up the boundary scan cells either to sample values moving into the device or to preload known values into the output boundary scan cells prior to some follow-on operation. When the ERD cells is set to 1111, the bypass is initialized. The last instruction is when the ERD cells is set to 0110, and this is the override instruction. The optional override instruction meant we had to modify the circuit a bit. We added a multiplexer to the BS cells, a little logic to the instruction decoder, a signal from the decoder, a multiplexer in the top level, and an override register. We opted for 12 cell solutions containing both data and instruction for override. This means we can force any number of the BSLs to any value you want, giving us a lot of flexibility. Each BSL is connected to 2 override cells, 1 instruction and 1 data. The control signal is combined between the override on and that the other bypass on, xtest on is off. This lets us keep the values in the override register and test the circuit as normal with any BSL overridden. We choose the 12-cell solution to give us flexibility of overriding everything and to save some clock cycle using 2 6-cell solution, 1 for instruction and 1 for data. Reset the BST infrastructure and check that the system output follows the logic value driven to the system inputs. We are assuming that the core circuitry is simply a set of identity function. We now shift in the xtest instruction and check that the system outputs no longer follow the system inputs. Then we remain in xtest and shift in 6 ones to set the 3 data outputs to 1. Assume that the rightmost bit is the first bit to be shifted in. Now we shift in the bypass instruction and check that the BSLs return to transparent mode.
This is the test bench for the override instruction. Here you can see our override cells. So we have 6 data cells and 6 instruction cells. So we set the cell instruction for 1 and we are going to force that to be a 1. You can see there that we have shifted into the override on stage, and you see that we force the value in these 2 outputs to be 1. When we go into bypass, you say it still is high here until we back into the reset stage where override it goes low, and the 2 outputs drops down to the normal state and we stay in the bypass mode.